This is tutorial one. No. This is lecture one. Okay, I'm going to play the lesson. PowerPoint, since it's a self-animated voice, I will just run through. And of course, at certain point, I might pause to do some explanation if I need to. But if not, then upon completion, if there's some time, you all want to ask question, please ask. Please clarify your doubt. Okay?
Hello, everybody. This is
Can you all
Mr.
hear the
Teo,
audio?
your module leader for EG3959. Instrumentation and supervisory
The audio
control.
for the
The
PowerPoint.
purpose of this module is to give students a good grasp of the theory and concept behind instrumentation and control. After going through this module, students will be in a better position to appreciate, understand and analyze things and processes happening in a plant. Example: a power plant, petrochemical plant, etc. To start off, let me briefly go through the overview of the module. Referring to the module overview page in the blackboard. At the end of this module, students will be able to interpret the process operation and select appropriate measurement and control devices for a process plant using instrumentation techniques. Students will be able to describe and analyze the characteristics and performance of a control system based on control theory. Students will be able to choose and apply different types of measurement and control techniques used for process control. Students will be able to formulate appropriate PID algorithm, simulate and implement controller for process control using LabVIEW Virtual Simulator. The in-course assessment for this module is practical 30%, which include a lab test and 3 lab submissions. E-quiz 25%, assignment 20%, and end of semester test 25%. Referring to your lecture notes in Chapter 1, page 1 to page 5, it gives an introduction and overview to instrumentation. Examples of instrumentation widely seen in power transmission, power generation and power distribution as illustrated in Figure 1-1.
Okay, this part, Chapter 1 is basically an introduction. So usually you will not be tested on Chapter 1. But because it gives quite a broad introduction on EE stuff, like for example, power transmission and power generation and power distribution. So we need to go through certain thing about it. But then by and large, it's trying to say that in all this power transmission, power distribution and power generation, there's a lot of instrumentation involved, right? There's a lot of instrument which you got to control, you got to read, you got to sense, etc. So therefore, it is telling you that the vast, huge skills of setup in all these kind of power transmission, generation, and distribution, which you guys may be more familiar than me because I'm not an electrical engineer, right? So therefore, that's what basically Chapter 1 is all about, is to link the concept of instrumentation with your module. Okay?
Most importantly for this chapter, we want to introduce students to the process control overview concept, as demonstrated in Figure 1-2, which will be further discussed in the future chapters. A process control starts off with a desire of controlling the output variable of a plant. The plant comes with the interference and disturbance from the environment and other unwanted sources. To control the output of a plant, which is the control variable CV, we got to measure CV and convert it to a process value PV via the measurement element. This is in turn compared to a set point SP. Error is produced by subtracting the SP with PV from the measurement element. This error is then fed into the controller. Controller will then generate a control signal CO to steer CV closer to set point SP via controlling the control element, and the whole process repeats itself.
Okay, this is a very broad view of the entire control process. You will be visiting these blocks many times. In fact, each of the chapter will be trying to, in fact, Chapter 2 will be touching mainly on measurement element and of course some of the processing. And this is basically chapter 5, I think, chapter 4 or 5. And then this is etc. So few of them will be break down into each. But then by and large, it will be all in a closed loop kind of control. Because in order to control, you have to have a closed loop, to feedback loop to understand what is happening at the ground, and then taking the difference between the reference and the actual measurement, and you create an error. And then through this error, you generate a voltage that's supposed to bring it up or down. Take, for example, let's say right now I'm trying to control the temperature of the aircon room. So temperature aircon room, my desired temperature, let's say, is 25 degree, but right now it's 30 degree. So you look at the environment, it reads 30 degree, it put down here, say that 30 minus 25, it's 5 degree higher. So 5 degree higher, you tell the controller there's a 5 degree difference. So the controller will pump the fan, decrease the temperature, and then you try to reduce the temperature, etc. So you go on, loop until it reaches the set point. But of course, it doesn't stop hitting the set point, because it will go below the set point and then go up again, below, go up again. And that's how control process usually work. Ken?
In Chapter 2, we will be discussing more on instrumentation. For many real and practical processes, it involved many instruments that are deployed in the field. They are used to either detect or sense various process parameters like temperature, pressure, level, flow, etc., and convert it into manipulatable control variable. In most process control, instruments utilized are broadly classified into measurement element and control element. For measurement element, it is made up of 3 subcomponents, namely the transducer element, the intermediate modifying element, and the data presenting element. On the other hand, for control element, it is made up of 2 subcomponents, namely the transducer element and final control element.
So largely in any of the instrumentation setup, it will be very complicated, a lot of valve, a lot of tools, a lot of display. So broadly speaking, we want to, we are really, if you want to take control of the entire process, we are more interested in the measurement element and the control element. Measurement element is basically, in short, it encompasses a transducer element, which means that it sends the actual, let's say, temperature. It sends already, but you cannot directly process temperature. So therefore, you got an intermediate modifying element, which convert the temperature, say, to electrical reading. And then a data presenting element, which convert the electrical reading into some form of digital display, for example. So this is what we call a measurement element, which allow you to have a view or a scope view to see or diagnose what is happening to the system. So this is what we call a measurement element. But on the other hand, the control element is different. Control element is something like valve. Let's say, for example, I am controlling the flow of the water through this pipe, and then I want to really have some control. So therefore, it will make up of actuator and the final body of the valve. So if I turn in the valve actuator, I will slow down the flow. And if I counterclockwise and release the valve and make the opening bigger, then the flow will be smoother. And that's how my transducer, or the actuator work. And the final element is just the casing of the valve. Okay, so far so good,
Actual processes refers to picture on the left. May be tedious to put it on paper. An equivalent diagram is being developed for engineers to put down the details using standard symbols and abbreviation. This diagram is called the P&ID, piping and instrumentation diagram, as illustrated in figure 2-3.
Okay, this diagram, in short, pretty simple. It's to tell you that the instrumentation make up of a lot of equipment, but if you try to draw it, maybe take a few months just to come out a diagram, and then by the time you communicate with your department engineer and manager, game will be over. So therefore, to simplify stuff, engineers like to simplify things into symbols. So you use symbol to represent the entire process, and this kind of symbol is what we call the piping and instrumentation diagram. In short, we call it a P&ID diagram, piping and instrument diagram, right? So you use symbol like that to represent the actual instrumentation setup. But it's the same thing. For the engineer, they prefer to look at it this way because it's simpler to look at, right?
For P&ID diagram, the explanation can be easily found in the table P&ID symbols in the formula sheet that is provided. For abbreviation,
Sorry,
figure 2 dash.
Sorry. I want to stop it, but because I clicked too fast, all the voice come up. So what it means is this particular sheet here is inside your formula sheet. Just now I show you the formula sheet, right? It's inside there. I will restart this page again.
For P&ID diagram, the explanation can be easily found in the table P&ID symbols in the formula sheet that is provided. For abbreviation, the meaning of the first letter is on the left of the table, while the meaning of the subsequent letter is on the right of the table. For field locally mounted, it is represented by a full circle, whereas the panel mount is represented by two semicircle. There are numeric number in each circle. This number indicate the process ID. Line draw for electrical signals. Pneumatic signals and process flow signals are represented by different styles.
So in short, this row represent the first number, first alphabet. So first letter here will be, let's say for example, it is F, right? You can see F here, right? F means flow, right? You look at it, flow, right? But the second letter is no longer using this row here. It's no longer using this column. Is using this second and third letter is using this one. So this is flow T. T is transmitter. So it's a flow transmitter. So it transmits the flow information. Okay. So that's what this short form means. And then what is this circle and semicircle means? For example, this is a full circle. It means that this equipment is field or locally mounted. So it's mounted in the field. Whereas this one is with a dash in between. This is mounted in the panel. It means in the control room. Okay. Now, what about the lines? This line is dotted. Dotted means it's electrical signal, right? Now, if it is dash with two slash right here, for example here, this is called a pneumatic signal, right? Of course, the darker one will be the process signal, right? Process flow here, process flow line. So these are process flow line. Okay, so far so good. And of course, there's numbers here. Can you see number 100, 101? These are the individual process ID because there is so many process loop. For example, this loop is measuring the flow, right? So the whole process, they don't call it a flow 1, flow 2, too many names to name. So they just use name number just as a process ID. So this is 101 process, this is 100 process. This is measuring temperature. Can you all see? All TTT here. So it's the temperature valve. This is temperature indicating controller. This is temperature transmitter, and this is temperature E. E is ABCD. This is the temperature sensor. Okay. Okay. Now this is always come out in the test one. So this is quite important, but this is a question where people can score a lot of marks if you know how to read the table, reading the table and interpreting. So it's very easy to score. And in fact, this is a giveaway mark.
Figure 2-6 on page 6 illustrated an example of measurement element. A Bourdon tube pressure gauge with digital readout. This element is used to measure pressure at the input. The transducer element will convert the pressure into small voltage V1 before handing it to the intermediate element. The intermediate element will process V1, amplify for this case into V2. V2 is then passed into the data presenting element, digital voltmeter, to convert the voltage from analog V2 into equivalent digital output.
So this one, need not worry, it's just to show you how an instrumentation instrument called the Bourdon tube pressure gauge works. It basically read inputs and then convert it into voltages, right? So this is a transducer element, change the form from voltage to, pressure to voltage. Then the intermediate modifying element is actually amplifying, making the voltage signal larger. And then the data presenting element is converting it from analog voltage into a digital representation, where you can see the digital display. And of course, all of them are supplied by external supply here. So this is the maybe the electrical wiring, how it's being wired, and these are the block diagram. So, okay.
Here is an example of an instrument with subsystem. It relates to a flow meter reading in flow rate, converting it into differential pressure, then into current, and finally into needle angle on dial. The question wants us to calculate the output angle when flow rate is 0.0004 meter cube per second, and also the output current for flow rate of 0.0004 meter cube per second.
So basically, this is one example in your lecture notes, in your detailed lecture notes, whereby it talks about this system, whereby it measure the flow rate and then it output actually the needle diffraction in terms of theta and the output currents in terms of from 4 to 20 milliamp. Of course, through it, there is some conversion. They will convert the delta P based on the Q. That means from your Q flow rate, you will calculate what is delta P by this differential pressure meter. And the formula given for delta P is 2 times 10 to the power 6 Q squared. And then when the delta P is presented here, it is again converted into current, and the formula for the current is I equals to 20 delta P. So put in 20 delta P times delta P times 20, you get current. And then current going into here, 14 of I will give you theta. So the deflection angle is actually 14 times of current. And then of course the current itself is directly being pumped out here as the output current. So what they want you to calculate is calculate the output angle if the flow rate is 0.0004 meter cube per second. So flow rate is Q, right? Q is 0.004. What is your output current? So it's asking you what is I, right? What is I? If you know Q, what is I? So this is quite straightforward, right? And calculate the transmitter output current for the same flow rate. So they also they want you to calculate these are basically the angle and the current, right? So they want to know what is theta and what is I. Okay, so the next slide.
Using the formula gotten from the question, output angle theta is 14 I is 20 delta P, and delta P is 2 times 10 to the power of 6 Q square. Since Q is 0.0004 meter cube per second, we substitute that in, and we yield theta equals 89.6 degree. Similarly for part 2, we can solve I to be 6.4 milliampere.
Part 2 is just calculate up to here. They don't put in the 14, the further all the way to theta. So they just use 20 delta P. Yeah?
There are many real-world parameters we want to measure and control, one of which is temperature. Temperature measurement can be made using the changes in the material property when subjected to heat. This change in material property can be either change in thermal expansion, change in contact potential, change in electrical resistance, or change in pressure. For temperature measurement, we are only going to touch on 2 senses, that is based on change in contact potential and change in electrical resistance. Figure 2-9 shows an example of a sensor thermocouple that changes its contact potential when subject to different heat intensity. In general, the equation that relates and explains the thermocouple action is given as Vm, which is the measure voltage, is equal to the VTC, which is the voltage at thermocouple, minus by VCJ, cold junction voltage. More example of the concept will be re-illustrated in tutorial 1.
Okay, so this is a thermocouple which uses the difference in the response of the different material. It generated basically a thermocouple voltage, which is they use a chromium and aluminum, right? So after that, you will have a measured voltage. But because there's a co-junction, and the equation that relate the V measured with the VTC and V co-junction is these two voltages, or they call it VCJ. And that will be the equation. So for now, we just stop at this, but we just know that a thermocouple is just a 2 lead, 1 tips, which is the difference in terms of material to detect the thermal voltage. And we will come to this in tutorial 1.
For now, please watch the video on thermocouple. Yet another sensor for temperature sensing is the RTD, resistance temperature detector. This device changes its electrical resistance when subjected to different intensity of heat. The equation that governs the RTD is RT equals to RT0, resistance based on temperature 0 degree, multiply by open bracket 1 plus alpha, temperature coefficient, multiply by temperature close bracket. RTD exists in forms of 3 wires and 4 wires type. Each type are chosen based on the sensitivity of the measurement over the line resistance.
So by and large, RTD has the characteristic of temperature changes with temperature. Right? When you experience different temperature, based on the equation, it will change. Of course, it has a base temperature at 0 degree. What is the resistance? And this is how it looks like.
Please also watch the video on RTD.
We may not have time to go through the tutorial for right now. So for N1, N2, probably
Hi, I'm Josh Bloom. Welcome to another video on the RSP Supply Education Series. If you find that these videos are helpful to you, it certainly helps us out if you could give us a big thumbs up and subscribe to our channel. In today's video, we are going to talk about a device that is used commonly in industrial applications for collecting temperature data. I am not talking about a thermistor or thermocouple. I am talking about a resistance temperature detector, or sometimes commonly referred to as an RTD. An RTD is a type of input signal commonly found in industrial monitoring situations. The same types of situations where you might find basic digital and analog signals coming into a PLC. Much like those digital and analog signals, depending on the PLC hardware that is being used, you can also input RTD signals into the PLC accurately to read temperature data in many different applications. In this video, we will talk about what hardware makes up the RTD and how it works. We will also discuss some of the reasons RTDs are used instead of other temperature devices such as thermocouples or thermistors. At its core, RTDs use a specific type of metal that, depending on the resistance measured in that metal, can determine the temperature. The actual measurement occurs at the element, which is a portion of the device that actually is able to collect the data needed to provide accurate temperature readings. There are many different types of RTDs, some more common than others. A few examples are, first, the thin film element, which uses a very thin layer of resistive metals adhered to a substrate, typically ceramic, then coated in glass or epoxy. Next is the wire wound element. This type of element can provide greater accuracy and wider temperature measurement ranges, however, can create stress on the element wire, which can lead to slight measurement errors over time. Lastly is the coiled element, quickly becoming the most common type of RTD element. The coil element combines ideas from the two previous types as well as additional design elements. This element allows for strain-free measurement on the element wire while still providing very accurate measurements. So how do these different RTD elements actually work? RTDs work off a very basic principle, which is the correlation between metal and temperature. As the temperature of the metal increases, the metal's resistance to allow flow of electricity increases. So it stands to reason that as the temperature of the RTD resistive element increases, the electrical resistance measured in ohms also increases. Understanding this resistance and its relationship with heat is what can give us an accurate temperature reading. Each metal has a certain resistance measurement at different temperatures. So based off the resistance that is measured in a given type of metal, we can determine what the temperature actually is. The most common type...
Okay, for N1, N2, I think your times is up. But I want to caution you one thing. This whole lecture notes you can go through by yourself, but when you play the lecture notes, please make sure that there is no VPN on. You all know what is VPN is, virtual private network or something like that. So if VPN is on, you cannot access the YouTube link.
Watch for this week. Please go through also the e-tutorial one.
So for this week, for e-tutorial 1, we will be going through P and ID diagram, question 12, question 1 on measurement and control element, and question 2 on the control element control valve, and question 3 on RTD. Okay, let's at the back of the after this page, there is tutorial that is being pre-recorded, but because it's being pre-recorded, I will not go through using the video, but rather I will just take out the tutorial sheet and discuss on the question. Okay, let's look at the question right now. Let's look at the question of the tutorial. Let's look at the question on the tutorial. Where is the question? Blackboard. Okay, if you go to the tutorial site, I'm opening the PDF, right? So the first question we want to do is question 12 on P and ID, right? P and ID. So let me scroll to question 12 first, then before I share the screen. Okay, this will be the question 12, with a P and ID diagram shown here. Now, so it says that identify the instrument and their location in the P and ID as shown in question 12. So what are the instruments involved? There are actually 4 instruments, 1, 2, 3, 4, right? And we know that these are easily understood, right? What is identify an instrument means that telling you using the abbreviation, what is this instrument, right? And the location meaning that is it field or locally mounted or is it panel mount? So let's try and see it from the other point of view, which is where the lecture notes, we have the P and ID diagram, right?
For P and ID diagram.
Let me access, instead of that, let me access the formula sheet, and go to the P and ID diagram instead. Can you see the formula sheet? Yes. This is a P and ID diagram formula sheet. And then, of course, if we go back to the tutorial, where's the tutorial? Let me hide this thing. Okay, tutorial is over here. So let's see this guy, TY. What is TY? TY means, can see from the formula sheet, T means temperature, right? The first letter is temperature. Y means relay or converter or whatever. So it's a temperature. TY means is a, can you see here? TY means a temperature relay. Now this is T again, so it's a temperature, TIC. I is indicator for second letter, indicator, right? C is controller. Third letter also the second column is controller. So it's temperature indicating controller for the second one, right? Now what about TT? TT will be temperature transmitter. The second letter is transmitter, right? So you can see TT is temperature transmitter. Now TW on the other hand will be temperature well. Oh, Ken, so far any problem with naming the abbreviation? Any problem? Anybody got difficulty following?
No.
No, huh?
No.
So now we go to the location. A lot of you just remember to name the abbreviation, but you've forgotten about their location. Now location means whether it is a full circle or semicircle. Huh? So you look at it, those full circle will be field or locally mount. Those semicircle will be panel mount or instrument mount, or panel mount instrument. So therefore, you just answer this accordingly, for each of these instruments. So that is for question 12. So no problem, right? For question 12. Any question on that? Question 12?
No.
No. No.
No.
No.
Let's look at the next question, which is question 1, which we are going to discuss. Question 1. Question 1, can you all see the question?
Can.
Question 1, define a transducer. Name 3 components for measurement element and 2 basic component for the control element. So this is already inside your lecture notes, right? Define a transducer. A transducer is basically some device that conduct from one form to another. For example, a pressure to electrical or something like that. That's what we mean by a transducer, right? Now, the 3 main types for measurement element, what are they? Remember the lecture notes just now we saw, right? Let me go to the page. Where's my share? Can you all see? Measurement element, there's 3 types, right? One is transducer element, intermediate modifying element, and data presenting element. For control element, there is transducer element, final control element. Okay? So this is a theory question, very straightforward, right? Very straightforward, right? So this answer all the 3 already, yeah? That's for question 1. Now, how about the next question? The next question we are going to talk about is the question 2 on control element, control valve. Question 2. Let's look at the question 2. Let me stop sharing. I also a bit blur which screen I'm sharing now. Question 2. Given a relationship between the signal percentage and milliampere, an electronic loop controller output 8.55 milliamp. So this is the range of output it can produce 4 to 20 milliamp. But now it is outputting 8.55 milliamp to a direct corresponding control, where 4 milliamp means totally shut, and 20 milliamp means wide open. So how far should the control valve be at this signal level? So it's asking you what is the percentage of opening at 8.55 milliamp. So how to calculate this? Anybody, any idea?
You take
Anybody?
8.5 divided by 20 milliamp.
You want to show, or I can pass the screen to you? You want to share or what?
Oh, no, it's okay.
Or you want me to share with you guys?
Yeah, sure.
Let me see. Can I get the? Hey, how come I cannot get the writing screen? Okay, I put a Word document. Easier. I put a Word document so that and I share the Word document. Okay, so it says you all should be able to see the screen, right? Can you all see the screen? Can, So if I put to draw, right now, it says that 4 milliamp. 4 milliamp means what?
Totally
4
shut.
milliamp totally shut means that 0%.
Yeah.
0% of opening. So then the other one is 20 milliamp means totally open, right? So it's 100% open. Now the question is, what is 8.55 milliamp? Oh, can? So how to solve this question? So on one hand, if I draw a charge, this is 4 milliamp. And if I draw another one, this is 20 milliamp. Right? So this part here is 100%. This part here is 0%. Now, of course, you have 8 point something percent, 8 point something, 8.55 milliamp. And this will be a linear straight line, right? I mean, I try to as straight as possible. What is this? Very straightforward, right? Now, first thing you can see that there is a triangle, right? There's a triangle. Can we solve a similar triangle?
Yeah,
Now the first triangle, if we say opposite over adjacent, what is it? 20 milliamp minus by 4 milliamp over 100, right? 100%. This first triangle, right, must be equals to the slope of the second triangle. Second triangle will be 8.55 milliamp minus by 4 milliamp divided by, I don't know what is this. So this must be x, x minus by 0. So I call it x, right? So if I find x, x means what is your percentage opening, right? So now if I do this, I will have this equals to 8.55 minus by 4 over 20 minus by 4, right? Times by 100. X will be equals to, anybody have a calculator? Should give you about 28.4%. Okay. Any question for this? Valve opening. This is just a simple straight line calculation. Any question? Can you all see my share screen or not? Can?
Yeah, can.
Can? So this one no problem. So no problem. Shall we go to the next question? Next question will be on RTD. RTD is slightly more difficult, but let's go to question 3. Just now, as the video said, let's share again because I don't know which screen you are at. Now let's go to question 3. Question 3 says that a platinum probe with actually RTD is not that difficult. It's the thermocouple. A platinum RTD. So the material for the RTD is using platinum probe with 500 ohm resistance, PT 500 characteristic, and the alpha approximate about 0.00385 per degree Celsius, and determine the resistance of RTD at 100 and 1000. So this is very straightforward. If you go to the words document again, where is my screen for writing? Just now my screen for writing disappear. Let me stop share again and I share again. Just now I'm using whiteboard. Let's erase. This one you all need not? Do you all need this screen? You want to screen capture or you want to take a picture? Can answer me?
I think it's okay.
It's okay, yeah? You can redo it, yeah?
Yeah.
Okay, let's go to the... Should be quite straightforward, first tutorial. Nothing much. Okay, now the question for the RTD is, what is your R? R is equals to RTO, right? 1 plus alpha T. That's your R or R bracket T lah. Oh, so this is the resistance of the RTD at RT0, which is 0 degree resistance, times by 1 alpha. What is alpha? Alpha is given as 0.00358 per degree C, right? So this is given as 0.00385. 358 or 385? 385 per degree C. So alpha is given, right? They want you, and then the resistance at nominal temperature, nominal resistor is 500 ohms. So this is 500 ohm. So this is 500 ohms here. So they ask you to find what is R when T is equals to 100 degree. So you just put in 500 times by 1 plus 0.00385 times by T is what? T is 100. So you just put 100. If you press the calculator, you should get what? 692.5 ohms. Right? Now how about R equals to 1000? When T equals to 1, R when T equals to 1000. So T is equal to 1000, you get just 500 multiplied by 1 plus, again, same formula, 0.00385 times by 1000 now instead of 100. So here you get about 2425 ohms. So this is for part A. Part A, question 3, part A. Okay, now they say if a small current of 0.5 milliamp is used to drive the RTD, determine the voltage across the RTD. So if you know that this RTD changes from 692.5 ohms to 2425 ohms, and if you pump in a 0.5 milliamp current, now what is your voltage? V. So they ask you what is V. So V must be equals to 0.5 milliamp, right? Times by 692.5 ohms, right? Which give you 0.354. Okay, that's one part. Now that is for 100 degree. Now how about V at 1000? V at 1000 will be again 0.5, but this time you multiply by 2425, which give you 1.213 volt. Okay, so that is for question 3. This is part B. Any question on that? So far, so good. Any question? So that finish up all our tutorial question. If you still cannot catch what I'm trying to say,